This is an introduction to Har Bal 3.7, illustrating the feature set it provides for the purpose of mastering recorded music. Let's start by opening a track to master. When Har Bal opens a track for the first time, it performs a comprehensive analysis of the track. It does so by breaking the track into short segments at a nominal 50 millisecond time interval. It then creates power spectrum estimates for each of those segments using Fourier transforms. It uses a window of 16,384 points in length to obtain the spectrum estimates and then bins the results in 1/12 octave frequency bins centered on the 12 pitches of equal temperament tuning common in Western music. On a 50 millisecond time step, 16,000 points typically provides a lot of overlap between adjacent time steps. This results in a greater computational load and consequently slower analysis than the non-overlapped analysis in Har Bal 2.3. But it is necessary to obtain the time resolution required for things like real-time spectrum display, track splitting, and complex time selection provided in Har Bal 3.7. Also, that number of points is required to obtain a good low-frequency resolution in the spectrum estimates that complements the resolution of the 8,000-point finite impulse response filtering that Har Bal uses. When it produces spectrum analysis information, it does so for the left and right channels independently, as well as mid-side representations of the same signal. For the time domain, Har Bal uses non-overlapped data window at the same 50 millisecond interval to calculate the average and peak power values for the left, right, mid and side channels. All this information is then stored in a file on disk, thereby containing a complete time frequency domain representation of the track. It also stores the spectrum data in a representation suitable to be able to quickly determine time selections for the complex time selection feature, which I'll introduce later. Returning to Har Bal, you can see that it shows the track timeline at the top and the spectrum information in the middle of the app window. For both, it shows the average levels in green and the peak levels in yellow. For the spectrum, these can be toggled on and off using the toggle buttons in the bottom right-hand corner. The spectrum view also has a real-time trace in purple, which can also be toggled on and off. To the left of the spectrum view, we find a drop-down list which you can use to select which spectrum to view, either mid, side, left or right. You'll note that on first opening a track, the view defaults to the mid view. This is by design because typically you will do most EQ editing in the mid view, as this view shows the spectrum for the whole track, and any filter edits done in this view affects left and right channels equally. This is so because the mid-channel edits are applied to the side channel as well. Remember that mid is simply the left and right channels added together, or mono if you like. You can alter the display resolution for the spectrum from 1/12 to 1/6 octave to 1/3 octave to 1 octave resolution. This can be useful to get a clear idea of how the spectrum balance might sound. The 1/3 octave view in particular roughly corresponds to how we hear the track, as the critical bandwidth of human hearing is nominally 1/3 of an octave in width, except at low frequencies where it's wider. To the right of the drop-down list, the S button allows soloing of the spectrum in view when playing the track. If we play the track and listen to the outcome, you'll get an idea of what this means. Below there are three sliders: volume, gain and air. Volume is simply a master volume control for monitoring playback and has no effect on the mastering signal chain, only playback. The gain control provides extra gain prior to the Har Bal limiter. The air control provides hash zone ambience processing that can be useful to glue the component parts of a mix together in cases where the track lacks a sense of spatial connection. It's now worthwhile looking at the filter structure in Har Bal to get an idea of what is going on in the signal chain. First, we have independent left and right channel filters, which are accessible through the left and right channel spectrum views. The outputs of those filters then get transformed into a mid-side representation, mid being the sum of left and right and side being the difference. These are then filtered by the mid and side channel filters, but you should note that the mid filter is applied to both mid and side. This is by design because we want the mid filter to act as a common filter for both left and right channels equally. The side channel is independent to allow us to alter the stereo image should we want to. This particular aspect of Har Bal has caused considerable confusion among some version 2.3 users who were under the impression that they had to create filter responses for left and right channels separately, rather than the much simpler process of doing most of the EQ in the mid-channel view. After filtering, the mid-side representation is converted back to a left-right representation and finally filtered by 4 air filters. These filters provide the hash zone ambience processing in the same manner as a stereo reverb unit does, although how the impulse responses are arrived at is different. This is illustrated here. To realize hash zone ambience that does not color the sound, Har Bal takes a flat frequency response and then applies a tapered log normal random deviate to the response. It then transforms it into a minimum phase impulse response. This results in an impulse response confined to the hash zone with no pure time delay and no early reflections. The tapering of the deviate results in an effective reverb time for higher frequencies shorter than low frequencies, making it sound more akin to natural ambience rather than synthesized ambience. This behavior happens in natural environments because high frequencies tend to be absorbed more than low ones. Returning to the software. Above the spectrum view, we see 3 tabs: spectrum, frequency response, and histogram. Clicking on the frequency response tab shows us the actual frequency response for the corresponding filter in the signal path block diagram. As we haven't done any editing yet, the response is flat. The histogram view shows a histogram of the average and peak level in the timeline. If you don't know what a histogram is, put simply, it represents the probability of something occurring, where in this case the something is a metered level of, say, x dB. This level corresponds to the x-axis value in the scale at the bottom of the bar graph. It has a range from -90 dB to 0 dB. The axis on the left-hand side shows the probability of the corresponding level occurring. So if you look at the average level trace, we see that there is no signal above about -13 dB and no signal below about minus 59 dB, because the probability values are 0 for these levels. I should point out that Har Bal excludes data at a level more than 75 dB below peak in the analysis phase to ensure that the analysis results aren't affected by how much silence is in the track. The peak probability occurs at around minus 36 dB, where the track average level spends about 5.6% of the time there. With a histogram representation, you can immediately see the dynamic range of the track, something not immediately obvious with level metering approach. Another way to look at the meaning of a histogram representation is to imagine a lead level meter, which only ever has a single lead lit, the one corresponding to the level at that time, and it has one lead per dB step, in a level from minus 90 dB up to 0 dB. The histogram at any given level then measures the proportion of time that that chosen LED is lit in the entire track history. Like the spectrum average, it gives an informative and concise method of summarizing the dynamic characteristics of a track. It gives an immediate picture of track dynamics that level meters just don't provide. Let's go back to the spectrum view and see what tools Har Bal provides for equalization. Looking at the right-hand side of the toolbar, there are a range of tools available to interact with the spectrum. Firstly, we have the navigation tools of zoom in, zoom out, and panning. The zoom tools work in two ways. Simply clicking on a region will zoom in or out by 50%, centering on the region clicked. Alternatively, you can select a region by clicking and dragging. The drag frame also applies to zoom out, but in this case, the corners of the current view are mapped to the drag frame as opposed to zoom in, where it's the other way around. Panning works by clicking and dragging. Imagine a sheet of paper on a desk and slide it with your hand. The pan tool works in a similar manner. To restore full view, we can use the Zoom All menu command or use the corresponding Alt-Z keyboard shortcut. Next, we have the harmonic cursor tool, which you can use to discover harmonic relationships in the spectrum view. If you click and drag the mouse over the graph with the cursor, a series of 10 crosshairs will track the graph. These crosshairs mark the first 10 harmonics of the frequency being tracked. If you look at the status bar, you will see that the frequency and level is displayed there. This corresponds to the value for the fundamental frequency, or the leftmost crosshair. You can find the values for the remaining harmonics by pressing and holding the number key corresponding to the harmonic while dragging the cursor with the mouse. Pressing 2, for example, will give you the second harmonic. Pressing 3 will give you the third harmonic. And pressing 0 will give you the 10th harmonic. You can toggle focus from the average to the peak trace by pressing the tab key while you're dragging. and the current edit focus is shown in the status bar here. That behavior also applies for the other editing tools in Har Bal. The next four tools are Intuit Cue, Intuit Match, Intuit Null, and Loudness Match, which I'll cover at a later time. Suffice to say, if you want to understand what you are doing and obtain the best possible results, then we discourage you from using these tools. Whilst they can be useful, they are generally targeted at users who want a quick and dirty result and care not for how and why things work. Finally, we have the spectrum editing tools: gain tool, shelving tools, and the peak taming tool. The gain tool is effectively a parametric equalizer. We use it by clicking it and dragging. The frequency at which we press down the left mouse button becomes the center frequency for the parametric EQ. By dragging up, we obtain a boost response. By dragging down, we obtain a cut response. By dragging left and right, we can alter the Q of the filter. The Q value is variable from 0 to 15, starting at a value of 15. The cursor shows a preview of the edit so you can see the effect it will have on the spectrum. The two extra crosshairs that you see to the left and right of the center frequency show the bandwidth of the parametric response. When you release the mouse button, then the change is committed. If you want to discard the change, press the Escape key before releasing the mouse button. This escape behavior is common to all Har Bal editing tools. Let's make a change to boost the mid-range of the demo drum track. You'll note a few things after the edit. Firstly, we can now see a set of grey lines that weren't visible before. These lines represent the original spectrum of the unfiltered track, which is useful to see as it gives a clear indication of how we have changed the track spectrum. Secondly, if you look at the top right-hand corner of the spectrum view, you'll see that the processed level number has changed. The average and processed numbers represent the average levels of the track before and after processing. But why has the level dropped with an EQ boost? Seems strange, doesn't it? Well, actually, it isn't that strange, and it has to do with loudness compensation, one of the key features in Har Bal that makes EQ much easier to do well. So what is loudness compensation? Well, it has no connection to loudness buttons on 70s vintage hi-fi amplifiers and doesn't do any filter modification. What it does do, though, is change the volume to compensate for the change in apparent loudness. Now, what do I mean by that? Well, in a more conventional way of mastering using a conventional EQ, a mastering engineer would adjust the EQ to taste while observing the levels on a meter, trying to keep the pre and post EQ levels the same as best he or she can. This goes some way to maintaining constant loudness, but there is a problem with this approach. How loud something sounds depends on the spectrum makeup because human hearing is frequency dependent. The ear is most sensitive to frequencies around 1 to 3 kilohertz and progressively less so at lower frequencies. Not only that, it is also subject to the effect of masking, whereby a loud sound in one band of frequency can completely mask the presence of lower intensity sound nearby in frequency. Har Bal attempts to account for these factors by using the Zwicker loudness model to determine how the perceived loudness changes with EQ, and then compensates to keep the perceived loudness constant. It uses a monitoring datum of 83 dB sound pressure level. This is important because the Zwicker loudness model attempts to model the human loudness perception across the full dynamic range of our hearing, but we want its perception to correspond to what is to be expected at moderate listening levels. By way of reference, the reference playback level for the THX theatre standard is 85 dB sound pressure level D weighted. The difference of 2 dB between Har Bal and THX standard is just a historic thing and largely immaterial to the outcome, as frequency selectivity of human hearing is almost identical between those two levels. Knowing this, we can now attempt to answer the question as to why the processed level has dropped. We boosted the level in the mid-range region where human hearing is most sensitive to loudness, but which doesn't have a lot of energy. Most of the energy in this case is confined to lower frequencies, which contributes little to perceived loudness. Therefore, the lift in mid-range raises the perceived loudness more than the drop in overall level of the track. This maintenance of level to keep constant loudness while EQing is part of what makes the conventional EQ approaches difficult. As a further demonstration of Har Bal's loudness compensation, consider this. With the gain tool, we can add a flat response edit and just provide gain by pressing and holding the 0 key while doing an edit. If we do just that and add 10 dB to the spectrum, see what happens to the processed level. Absolutely nothing. This is because we've made no change to the spectrum shape, so we've made no change to the perceived loudness, and the loudness compensation mechanism has removed the straight gain we added. That is why EQ in Har Bal is so much easier, because any inadvertent increase in the loudness level is automatically taken out. This means that our EQ edits don't suffer from perception bias of conventional EQ, where an EQ boost sounds better than an EQ cut because the level has been raised. Notice how the graph view looks cluttered and a bit confusing. When we do EQ edits, we can reduce this confusion by removing unnecessary plots. In particular, let's turn off the real-time trace by pressing the purple button in the bottom right-hand corner. Now the effect of our edits are easier to see. You can also turn off the original spectrum traces, but I generally recommend keeping them on in this view because they give an idea about mix intention, which I'll talk about later. Potential problems in track balance show up in both the peak and average level traces, so it's usually recommended to keep both on. This track is a good case in point. As you can see, a large peaking in the area of 100 Hz in the peak trace, which doesn't show strongly in the average trace. The cause of this and the remedy we'll discover later, but let's continue on introducing the other tools. Let's now select the low shelf tool and try using it. In a similar manner to the gain tool, we click and drag, but in this case, the frequency of the mouse button down location corresponds to the knee frequency, and dragging up and down will produce a linear boost or cut below that knee. Now select the high shelf tool, and we see it does something similar. But in this case, the boost and cut response occurs above the knee frequency rather than below. Both these tools are useful for modifying the spectrum extremes and also adjusting mix balance to taste. Now we can move on to the most complicated spectrum editing tool Har Bal has to offer, peak taming. What is it? What is it for? Going back to the problem peak in the peak spectrum trace, a track in general will have two issues that will require resolution as far as EQ is concerned. Firstly, in terms of the average spectrum trace, the shape it has and the balance between frequency ranges governs the color of the track, whether it is warm, cold, clinical or detailed. These characteristics are usually well reflected in the spectrum shape, though don't get into the mindset that there is one correct shape, because that would be a wrong conclusion. The ideal shape depends on the nature of the music, the type of the instrumentation, and the artistic intent. Ultimately, it is an artistic decision, not an algorithmic one. Although we can make some generalizations, as depicted in the figure. Good mix balance generally has a reasonably flat mid-range. How much tapering and the knee frequencies of that tapering will be a function of the type of music, the instrumentation used, and the artistic intent. Moving on, the other important issue in EQ is the peaking that occurs in the track peak spectrum. If the peak trace shows large peaks where none are shown in the average trace, it indicates that in certain infrequent places in the track timeline there are hot events. Usually, if left as is, those hot events detract from the quality of the track and can lead to listening fatigue and masking effects to the detriment of the track in general. In a conventional approach, these issues are usually tackled in a less than optimal way through compression, and in this day and age, particularly multi-band compression, which I am no fan of because of the audible artifacts it can introduce into recordings. This is where the notion of peak taming comes in. With the peak taming tool, I can draw a threshold line on errant peaks like so. Now look at what has just happened in the timeline. We now see grey bars showing the points in time where the signal goes above our threshold line. So simply from an investigative point of view, this feature is useful, as you can immediately discover what is responsible for the problem. Note the peak taming marker has 3 drag handles. The middle one allows us to raise and lower the threshold line, but preserve the slope and the horizontal position. The left and right ones allow us to alter the beginning and ending point. We can also delete peak taming markers by dragging them off the graph. But there is more to peak taming than just that. Note the circle with the adjust arrow symbols on the peak taming marker. This represents an adjust button. If we click on the circle, we then see a new spectrum editing window with a new spectrum display. This spectrum view is the average of just the points in time which exceed the threshold. Note how the average spectrum trace in this case is high like the peak trace. Here we can use static EQ to bring down that average level to something more reasonable and not affect the rest of the track, because the EQ only applies to the time selection. Let's do it. Now have a look at the original spectrum view and see how the peak trace has changed. It's now in line with the average trace. Peak taming only ever affects the part of the track responsible for the problem areas, whereas multi-band compression is continually affecting your track. That said, there are some skills to learn to use peak taming correctly and effectively to avoid audible artifact. But if done correctly, it usually can be artifact-free. As a closing point, note that the peak taming marker has a check mark below it. This indicates if the marker is selected. When selected, the complex selection is shown in the timeline. When not selected, the time selection is hidden. When you have more than one peak taming marker, this becomes important because you can only ever have one peak taming marker selected at a given time. Let's switch to the Frequency Response tab. Note that you can now see the shape of the frequency response edit we applied to the track. The same is true in the view for the peak taming marker. The normal gain and shelving tools as well as the navigational tools can also be applied in this view. Now let's return to the histogram view. Note how the histogram view has changed and we now see the original histogram in grey. This is the predicted change that Har Bal has determined based on our equalization, including the effect of peak taming filtering. Note that it is only an estimate and cannot be perfectly accurate, but the accuracy is typically to within around 0.5 dB. The reason why we can't predict the processed levels perfectly is because of how the frequency response affects power levels and how it depends on the nature of the signal components being filtered. In particular, it depends on whether the signal components are coherent or not. If coherent, then the components add on an RMS basis, whereas if incoherent, they add on a power basis. It is not possible to know the degree to which the signal components conform to either of these cases, short of carrying out the filtering in full. To obtain a reasonable estimate, Har Bal uses the average of the two cases to come up with a prediction. This theoretically, on average, gives the least error-prone result. We can demonstrate the accuracy by rendering the track as filtered, then opening the rendered result as reference. You can see that although the result isn't the same, it's in the right ballpark. Note that in this view we have an extra tool that we've yet to mention, the Dynamics tool. With the Dynamics tool we can place dynamic control nodes on the histogram. We place nodes by clicking and dragging. The level, which is the x-axis value at which the mouse button goes down, becomes the input level for the node, and the level at which the mouse button is released is the mapped output level. We can alter placed nodes after the fact by clicking and dragging the control nodes with the mouse. and remove nodes entirely by dragging them off screen. The displayed node represents mappings of input levels to output levels. With a combination of nodes, we can create a compression scheme. For compression, we would like to reduce the span of the main lobe of the histogram, squashing the extremes together. We can do that by using two dynamic nodes. The first at the rightmost extent of the histogram, which maps the input level to the same output level. And another at the leftmost extent that maps the input level to a higher output level. Here we try compressing with a 2:1 compression ratio. You'll note that as we drag the node, the status line shows the corresponding compression ratios to the left and right of the current node. Note how some of the compressed histogram has pushed past our rightmost control point. This happens because the speed of change of the compression gain envelope in Har Bal is limited to ensure that the dynamics processing sounds natural and artifact-free. As drum sounds are inherently fast and dynamic, the compression gain isn't fast enough to crush the dynamics, so some of the histogram pushes past our control point. To get a better understanding of how these nodes correspond to more conventional view of compression, consider this illustration. Here you can see how the node points correspond to the knee points and slopes on a conventional transfer characteristic representation of compression. Again, we can check to see how well Har Bal manages to predict the processing level by rendering the process track and opening as a reference. Again, the result, while not perfect, is close to the mark. Finally, we should discuss one further aspect to Har Bal, and that is the limiter. As with the dynamics processing in Har Bal, the limiter has been designed with the point of view of minimizing damage to transient material to preserve clarity. It does so by using a gain control signal that is filtered and as much as possible smooth. The limiter uses a conventional rectifier and attack decay processor common to traditional limiters, but also includes an extra low-pass filter to smooth the gain control signal. As this smoothing filter introduces a delay in the control signal, it is necessary to include an extra time delay in the signal path to ensure that the gain control is in sync with the music. However, it isn't a single limiter but three. A slow-acting limiter, followed by a faster one, and finally a catch-all one to clamp down on any short transients that make it through. The settings of each have been painstakingly optimized for the most neutral sound. By breaking the limiter down into stages in this manner, we can reduce the degree of limiting artifacts significantly. But there is still one more problem if aggressive limiting is attempted. If you have a strong and rhythmic bass component, whether from a synth, a bass guitar, or drums, it can result in a modulation artifact, whereby the bass modulates the amplitude of the other instruments in the track, something typically referred to as pumping or breathing. To minimize this intermodulation effect, we use three basic Har Bal limiters. One to limit the low frequency content, one to limit the high frequency content, and the final limiter stage to limit combined output of the two limiters. This approach allows the Har Bal limiter to be pushed very hard without obvious pumping. Note that we derive the high-pass signal by subtracting the low-pass signal from the complete input signal. This ensures that the frequency response of the limiter when not limiting is perfectly flat with no phase distortion. There is no limiter bypass because the limiter has no effect when not limiting. So there is simply no need for a bypass. Just lower the gain so limiting doesn't occur. Boosting the level with the gain slider will result in limiting when the rightmost edge of the peak histogram trace reaches 0 dB, which in this case has already occurred. From that point onward, any further growth in gain will result in progressively more limiting, as is indicated by the growth of the 0 dB bin in the peak histogram. Let's finish up by creating a mastering scheme for this example. First up, let's listen to what we've done so far. You'll note the mid-range of the boosting of the mid-range has lifted the snare out quite considerably. You'll also note the bottom end is tapering off above 10 kilohertz. For a drum kit, you would typically expect that it should be relatively flat beyond there up to about 16 kilohertz or so. So we can add that in for extra brilliance. Similarly, down the bottom end, the kick bass is a tad weak. We can add some extra kick to it should we want to hear those low tones more pronounced than before. Let's listen to those changes. It's clear from that there is a lot more detail in our equalized version as such. If we engage the third octave view, we get a better idea of the overall balance. You can see there's some weakness here, and in the peak trace there's also a bit of prominence of the snare, probably excessively so. We'll start by just addressing this weakness in this region. The overall balance is much better than before. In the original, the toms really stand out, which are actually responsible for this peak problem, the peak trace, but I generally feel that the snare sounds like it's standing out too much and a little bit fatiguing. We can attempt to address that with some peak taming. Note that I have to apply the peak taming to the original spectrum trace because we can't have it referenced to the filtered trace, because that would mean every time you make a filter edit you would change the time selection, which would really be difficult to manage, pretty much be unworkable and unusable. So peak taming references are always referenced to the original spectrum. Now, if we really want to be pedantic, we could also address this peak trace here. Now when we look at our third octave view of the track, you'll note that there's a nice uniform agreement between the peak trace and the average trace, which should make for a more pleasant sounding recording. And of course, when we listen to the final result, I think you'll agree that it actually sounds quite good. Perhaps maybe too strident for the snare drum still. So if you would prefer a mellower sound, we could make a minor adjustment by now just doing a global edit, bring that level down a bit. Perhaps a little bright at the top end as well. Could adjust that down somewhat. Then when we've finished, we can actually save our equalization scheme for future reference if we need to come back to it. We can render the final track. Now, as a example, we can actually confirm whether in fact the processing is, or the outcome of the processing is accurately predicted by Har Bal by reopening it as a reference. So as you can see, if we adjust this, you can see the average trace lines up pretty accurately with the prediction. The reason why the peak trace is different is because we've got the additional effects of compression going on, which we can't actually easily predict the outcome in the spectrum view, so that isn't accounted for because it's simply not workable to actually try and predict it. It would take way too much computational resources to actually predict it, and will make the software unusable. But it still gives you a clear indication of what the spectrum is going to look like. Similarly, the process level is in the order of magnitude that you would expect from its prediction. Again, not perfectly accurate, like I mentioned before, it wouldn't be, but it is within the ballpark. Histogram view, again, the prediction is similar but not exactly the same, because again, you can't do a perfect prediction with the information at hand without becoming very numerically intensive and CPU hungry. So we don't do it. We just give the best possible estimation with minimum resources, and it is perfectly usable in that case. So that basically concludes a first introduction to Har Bal 3.7 and the features it provides. Thank you.